for joining us today for QuSCo on Air session. So we will have a talk by Vadim Vorobev, who some of you already know as he joined us during our workshop in Padua in 2019. And so Vadim completed his PhD in 2017 in the group of Alexei Akimov, working jointly at the Lebedev Physical Institute of Russian Academy of Science and at the Russian Quantum Center. And during his PhD, Vadim worked on optical interfaces for NV Center in nanodiamonds, and then carried on with a postdoc in a startup company which was aiming for realization of NV-based sensor of magnetic field, temperature, and rotation. And since 2018, he joined Jörg Warthrup's group here in Stuttgart for a postdoc position, and he is now working in quantum measurement using NV Center in Diamond. And today he will share with us a bit of his expertise on this field. So Vadim, thank you again for joining us, and please go ahead.
Okay.
Perfect.
Thanks a lot.
Nice. I just wanted to present you really basic stuff. I think despite many interesting recent highlights and benchmark publications over the years in many prestigious journals, it's really still nice to understand the basics of what could be done within vCenter and how it actually relates to the conventional understanding of quantum theory, in particular quantum measurements, for example. So with that, I wanted to start, and yeah, you all know this new second revolution of quantum technology, and it's basically based on the fact that you now can use a high dimensional object instead of just two digital numbers. But if you, for example, take a look at the let's say cloud of words for the quantum computation, besides the big quantum, there are many other interesting words here. And in particular, I don't know, can you somehow see my mouse?
Yes.
Ah, you can.
Yes.
Yes.
Because I cannot. Okay. Then you can see two particular words which I marked here, which would be the topic of my today's talk. So I wanted to stress that despite many other interesting topics in quantum, the measurement is the main, let's say, the gateway to the quantum circuits and to the quantum machines themselves, because everything what happens to the quantum system happens inside, let's say, mystical quantum world, while we are classical observers, and in order to understand what's going on inside them, we have to measure them. So that's why I think this is one of the main things to understand, and it's still a subject to numerous debates in theoretical topics, and we will briefly talk to them today. Of course, despite that, we will also touch a little bit of quantum computation and quantum sensing. Okay. So how to measure a qubit? So if you ask Google, for example, how to measure qubit, they can immediately give you the talk of by Nielsen that you have to measure a number of outputs of zeros and ones of a qubit, and then basically estimate the probability to obtain 0 and 1. So this process is, you can call it empirical estimation of a qubit state. The problem of this process is that you destroy the qubit. And you have to start over every time. And over the time you average kind of the dynamics and you see the averaged evolution. It could be also done with ensembles or with single qubit, but in fact, in experiment, it's hard to realize such a system. And also, you could understand that with this approach, you can only measure at a time only one observable. Also, what is important is that there is a so-called intrinsic error associated to this process, which is based on the fact that your measurement is probabilistic. And such a measurement was first realized, we could say, by this famous Stern-Gerlach experiment, in which they sent silver atoms through the non-uniform magnetic field, which were then deflected either up or down. So this was the first demonstration of such a measurement, and it has huge consequences. And I think that's why, of course, they received a Nobel Prize later. But apart from the foundations for the theory to describe atoms, this is also interesting philosophical, let's say, Gedanken Experiment. Because this experiment shows you that if you measure, you basically project your system in one of its eigenstates of the measurement operator, which is called, could also be called projector, and the system stays in this state. And then if you apply several such measurements, every time the system will always give this same result. Of course, this measurement then led to the very big topic, which was succeeded by Isidore Rabi and Norman Ramsey, where they tried to then apply some periodic magnetic field on the path of these flying atoms, and then they could see that these peaks could vary depending on the applied periodic fields. And nowadays, these principles are very widely applied in medicine, for example, or in analytical chemistry. So I think you had a very nice talk about NMR and MRI applications. But such systems suffer from the fact that actually to detect single spin, you have to conquer with thermal fluctuations, because to read them out, nowadays you probe them with just a metallic wire, and you conquer with the thermal noise in this wire. So to overcome this, you have at least 10 to the 12 atoms for nuclear spins, and for electron spins a little bit better. But to ultimately go to the single particle level at room temperature, there is a need to go to the optical domain, because as you see here, at room temperature, the KT Boltzmann factor is much less than the optical transition compared to the EPR and NMR transitions. So the technique was evolved slowly, and around 90s, there was also a couple of PhD students from the Ramsey group. They established a new topic, which was related to the laser cooling and trapping of ions and atoms. So these systems could allow them to individually address single ions in the trap, which could be slowed down by laser fields. And this system allows for the first time to transfer actually spin, or in this case orbital momentum, to optical photon, so to say, to transfer it, to upconvert this energy and reliably read it out at room temperature. As for example, in our case, we know that after 2000 around, there was a big boom also in solid state spin containing defects, which are optically active. And in particular, we are talking today about the NV center in diamond, which has very nicely isolated energy levels for its electrons trapped within the band of the diamond, within the band gap of the diamond, which has very nice optical transitions. So these optical transitions, they possess these very nice properties that whenever you excite them, despite of which level you start, on the decay path, the states always tend to collect an electron spin 0 projection to the axis, and all other, they tend to go without any fluorescence or with a fewer fluorescence, so that you can see spin-dependent fluorescence. This also leads to the optical induced polarization, which could be used for other applications, but in our case, we will consider this to use as a spin readout mechanism. And of course, you can try to probe these electron spin transitions with microwave. And if you hit the resonance of that transition at the microwave frequency, you can see the drop of the fluorescence, which relates to this effect. But as we're coming back to my introduction, we're interested ultimately in the readout of the spin. And ideally, we would like to have a single-shot readout. And what a single-shot readout means. Here, I just mark it as a rule of thumb. I think also single-shot readout is more or less like jargon, that the signal-to-noise ratio in one iteration of the readout should be higher than 1. And this is quite tricky task to do, because whenever you probe the electron spin within V center, after a certain time, the fluorescence level is up to the steady state level, and also this leads, as I told you already, to the reinitialization of the electron spin. And this is a repetition of, let's say, 1,000,000 times of this readout, but per one shot you have only on average 0.1 photons for the dark state and 0.13 photons for the bright state. This results in signal-to-noise ratio of 0.05, so which is much lower than what is desired. To reach our desired signal-to-noise ratio, we need to repeat this procedure many times and make sure that the spin is not destroyed during this. Unfortunately, at room temperature with electron spin, this was not shown and this is not possible. But what is possible is to probe with such a scheme the nearby nuclear spin. And this was also realized at room temperature. So briefly, I will talk about this mechanism. If you look at the energy level schemes related to the NV center, having, as you saw before, 0 electron spin and -1 electron spin, you can also mention here the hyperfine structure related to the associated nuclear spins around. So the microwave transitions, which only drive spin-conserving transitions, would be selective then to the state of the nuclear spin. And if you hit, for example, only microwave 1, as depicted here on the left, and flip the electron spin with a pi pulse, as depicted here in the circuit, what you will end up is, if the nuclear spin is in the state 1 down, then it would result in the dark state of the electron spin, and vice versa. So what you can do with this, you can repetitively address this transition and ask in which state the electron spin is. Because you have to average many times the photons which you obtain from the electron spin. You repeat this a couple of thousand times, and in the end you obtain such a histogram. Here we have to be very careful how to interpret this. This is so-called the single-shot readout of the nuclear spin with electron associated with electron spin in diamond, and people also call it non-demolition measurements. and so on. But here I just wanted to clarify a bit that it's a non-demolition measurement if the state of the nuclear spin was already in the projected state. But if it was in some superposition state, first of all, you project it to some of the eigenstates of the measurement operator, and after that it stays there. So in fact, it's exactly this Stern-Gerlach mechanism in which, for example, if you send in some superposition state, already the first iteration of this protocol projects a nuclear spin, and every time you then apply this C0 and apply the green readout, you obtain same number of photons on average. So as a result, the sum of these photons results in this histogram, which kind of split. So this allows you to apply the sort of filtering. So you can attribute, let's say, on the next iteration of your protocol, you obtain, let's say, 90 photons, and you already know that your distribution looks like this. Then you can draw the threshold line and say, if I obtain next time 90 photons, I attribute this nuclear spin to be down, or otherwise, if it's higher than the threshold, I attribute it to be up. So this is so-called the maximum likelihood estimation of the projected state. And if you perform a series of such measurements and always make this filtering stage, you can say in which state your nuclear spin was at this measurement, in 0 or in 1. So this is a very important concept, and it was performed here in Stuttgart, also in Harvard, and in the group of Vincent Jacques in France, and I think in Montpellier, around 2010 till 2013, both on the nitrogen associated spin and nearby strongly coupled carbons. This concept is very important because it then led to the so-called universal readout of the electron spin, which, as we know, could be a very nice sensor of nearby species. So how you typically do it is having this unitary as any thoughtful sensing protocol, you can then swap the state of the electron spin to the nearby memory, and then you can apply this readout already to your memory. So this was also done here in Stuttgart, and this technique, it allows you to shorten the time, for example, of Hahn-Echo spectroscopy of the nearby bus. You can shorten this time from, let's say, several nights to just 2 hours. Yeah, so this is a very powerful technique. And as I already started to touch this topic, the NV could be thought as a very nice sensor, but this is the consequence of the fact that it is a single electron spin which is nano-localized, and it could be put in very close proximity to interesting objects. For example, some biological samples or some internal nuclear spin bus, which you can use as a register, something like this. But to make this happen, you have to apply sophisticated control to the electron spin. And in short, we call it DD, or dynamical decoupling. And I want you just to understand the simple concept of this dynamical decoupling, how it could be used to detect and control the nearby nuclear spins. So imagine you have the NV center as a central spin here, and a couple of nearby nuclear spins. And in the presence of large longitudinal offset field, all the couplings, all the hyperfile complex of the carbon spins will be much lower compared to this field. In such scheme, you can use so-called secular approximation, and you can expand your Hamiltonian for the nuclear spins conditioned on the state of the electron spin. Let's say if the electron spin in the state 0, you can apply just Bayer-Larmor precession, or if the nuclear spin, if the electron spin in the spin 1, you can apply the Larmor plus hyperphi. So in that case, what dynamical decoupling does is just it modulates this Hamiltonian between these two things. And if you go, let's say, into the interaction picture of the Larmor, detuned by the Larmor precession, you can find out that when the periodicity of this modulation equals the Larmor precession, let's say average Larmor precession, what nuclear spin sees is just periodic switching on and off of the transverse magnetic field generated by the electron spin. And this you can see as if you have just a two-level system to which you apply periodic field, whenever you hit the resonance of this two-level system, it starts to make a flip, to make a Rabi oscillation. And here it happens exactly the same. Of course, I put here very frightening formulas, but this is just to give the idea how, for example, you can simulate this. So you combine these time-ordered Hamiltonians, unitaries, which you then raise to some power depending on the number of applied pulses. But in the end, what you're interested in is that because all of these Hamiltonians are just rotations around certain axes, you're just interested in the net angle of rotation and the net axis of rotation. And so this you can pretty nicely solve with
Ask a quick question, is it okay?
Yeah.
About the previous slide, so I might be missing something, but so it seems like there's these Z terms which have different factors depending on the state of the NV center. But then this X term, it doesn't seem like you could dynamically decouple that away, or is there, or do you need like a more advanced dynamical decoupling process to
I
do
wanted
this?
here to exactly. So here we can talk, maybe yes, I missed this part, but here we can talk about the dynamics of the NV center itself, which is also interesting. For example, you can think of which dynamical decoupling you can apply to protect it from, let's say, from the bus, or from the Z term or from the X term. And we can talk about what happens actually to the nuclear spin during the dynamical decoupling. Because you have both this object in the consideration, in principle, you cannot neglect the dynamics of any of those. But here, we just say, okay, we drive our electron spin and we don't care about, for the moment, what happens to it. But we are looking at the dynamics of the nuclear spin.
Okay, that makes sense.
Yeah, so in that sense, what I wanted to put here is this H is actually the H which is acting on the nuclear spin. And it has these two conditions when the electron spin is in 0 or when it's in 1. So it's sort of like projecting operators, like the operators conditioned to the state of the other system. So does it answer your question?
I think partially, but maybe we can discuss it at the end again.
Okay, yeah. But it's a very important question, yes, in order to understand the further things. And yes, in fact, the complicated picture in this is that you can put all these formulas in, but the simple picture here is that if you just look at H1, you see that it has a Zeeman term, it has the perpendicular term, which is just additional Zeeman term, or parallel term, which is additional Zeeman term, and you have this perpendicular term Ix, which is just analogous to this B1 field when you drive just a simple spin. And if you switch H1 on and off, So you switch H1 to H0, back to H1. With a periodicity tau, you introduce the time-dependent Ix term, which drives your nuclear spin. So this is exactly what is happening, and you can see it here. What is depicted here is a solution of, if I ask, what is my net? So for example, this V0 and V1 are just unitaries, which you can present as exponent of the Pauli vector. So then you can expand it to different Pauli matrices, and this is what you get. So what I'm asking here is my component projected to Pauli matrix C and Pauli matrix X. So you see that normally you have Pauli matrix C, which is brown, and then when you hit a resonance, the Pauli matrix Z component drops to 0, and Pauli matrix X component goes to 1. Of course, it's normalized. So what you see here is that when you hit the resonance of the dynamical decoupling, your nuclear spin just starts to rotate with a certain radial oscillation speed. And this direction of this rotation depends on which the electron spin has been started in. So if the electron spin has been started in MS0, then it rotates to the positive direction, otherwise to the negative. So you can look at it as just a C0 applied to your nuclear spin. And you see that even resonances here, which are marked with yellow, they actually does not depend on the initial state. So the odd resonances depend on the initial state, and the even does not. So this gives you the ability to fully control your nuclear spin, even without application the resonant field to the nuclear spin and so on, just by manipulating the electron spin and correctly selecting this periodicity of this drive. And what it allows it to you is you can, for example, drive a nuclear spin. So here there's this example of three different NV centers. Either of those has different nuclear spins associated with this. And the orange does not have nuclear spins at all, it's just path. Blue has a very weakly coupled nuclear spin. That's why the modulation you create to drive it is not enough to surpass the decoherence. So you just see that it decoheres, but a little bit faster than the orange one. And the green one has actually quite strong aperpendicular component, which allows to drive it quite strongly. But still, it's very, very weakly coupled spin. And what we can also have with this approach is that going to these resonances, we can actually see different nuclear spins, because all of them split conditioned on the parallel component. So this could be seen because in the simple explanation picture, what I showed you is the H1 is just applying Ix, but it also applying Iz. And this Iz gives the contribution to the average Zeeman splitting of the nuclear spin. On average, it's just one omega Larmor plus 1/2 of a parallel. So the tau resonance actually happens at this particular value. Yes. Exactly. So this allows you to individually address different nuclear spins conditioned on the A parallel, and also fine-tune the interaction with it by applying different number of pulses and choosing different, so to say, rotation angle. What you can also do with this, so here you're looking at the diamond, which has a natural abundance of carbon-13 spins. And this is, let's say, the dynamical decoupling spectroscopy based on single NV center. it has at least 10 nuclear spins, which you can see here. But if you look at the isotopically purified diamond, which almost doesn't have any carbon-13s at all, you see that despite how good you're trying to resolve, and you maybe even go to the longest possible interrogation time, let's say here I went to the 41st resonance in this approach. The peak is still not yet splitted. So that means that you only see the resonance of the bus. And yet, if you apply this technique and change now the number of pi pulses, you can see such figure, which is here the D map, and you see that this resonant condition happens at 20 to 40. This number is not time, it's a number of steps of timing clock. But you see that here the resonance happens exactly at the position of the alarmer, but if you go away from there, you see some coherent dynamics occurring. And this coherent dynamics is actually the signature that we are looking at a single nuclear spin, which is slightly higher coupled than the rest of the bus, and you can interact with it coherently. Because if there would be no single nuclear spin, all the picture would be just flat and smooth. So we found such a nice NV center with a really weakly coupled carbon-13 nearby, and there is not even one carbon-13 elsewhere. And what we can do with it now? This is the comparative table which I make just maybe to analogy to those of you who are familiar with cavity QED and maybe superconducting qubits, that in superconducting qubits, the main working horse is, of course, the cavity and the photons, which are probing the two-level system inside such a cavity. So the main working mechanism is that you have a two-level system inside the cavity, and the photon, when it comes from the source into the cavity, reflects from the cavity and changes its phase. And then it's homodyne detected, and you are basically measuring the I and Q components of this photon, or let's say of this field. And during this, what you have is so-called dispersive Hamiltonian. So this Hamiltonian is represented here in the bottom on the right. So what it represents is that this H omega term is basically energy of the photon, and sigma z gives you the state of the two-level system, and n is an operator for the number of photons inside. So this operator, at the same time, it changes the splitting of the main quantization axis of the two-level system, depending on the number of photons. And what it also does is that it changes, depending on the state of the two-level system, it changes, let's say, the length of the cavity. So it changes the eigenfrequency of the cavity, which is represented in this H omega n. Yes. Due to this, and because of the fluctuations of the number of photons inside, so you're sending coherent light, the two-level system is being decohered. And this is the decay channel in this system, why, for example, you cannot measure infinitely the two-level system here and the back action here. In our system, as I already told you, we have NV center and the carbon-13 nearby, which we probe with dynamical decoupling. In our system, we have this interaction term, which only contains the SZ, which gives the phase offset of the NV center during the sensing, and IX, which leads to this rotation controlled on the initial state of the electron spin. So the IZ term we don't have, because the IZ term as I showed you, we cannot resolve and we can just neglect it. And so with this full analogy, we can just move on, and we can go and explore some interesting applications which were done already with superconducting qubits, such as looking at the non-locality paradoxes and, for example, apply Laguerre inequality to the sequential weak measurements. But also what this technique is powerful for is that it also allows you to increase the efficiency of your sensing of these particular nuclear spins. Yes, here I wanted to just give you a little bit deep understanding of what going on mathematically and how can one approach to this. So in particular, we are describing this protocol.
Maybe I have another question, if that's okay.
Yes, yes.
Going back to this comparison.
Yeah.
So with the superconducting qubits, it's known that the actual measurement, it's not really quantum non-demolition measurement, because in fact the Hamiltonian does not commute with the observable and only does if you take the rotating wave approximation. And this is why usually they put Purcell filters so as to avoid the increase of the decay, so the decrease of the decay time. Now, would you say that if I look at the full Hamiltonian for the system of the spin and the electron spin and nuclear spin, the actual observable doesn't seem to be commuting with the Hamiltonian? And is it then the dynamical decoupling that makes it commute? Is this the case? So does it become a measurement because of the dynamical decoupling?
So to answer your questions, I have to introduce another thing, but in principle, you're touching correct thing here. Just measurement on its own, just IX, would not be enough to see the full beauty of this. And what we also add here is precession between the two measurements. It's just a free precession. So let's say here with the purple squares depicted MI and MI plus 1. So between these two measurements, the nuclear spin just freely precess. And next time you apply the dynamical decoupling, you actually already measure something like IY plus IX cosine precession angle. So in that sense, we are measuring time-varying operator which does not commute with itself. That's one thing. Another thing is that you asked that our interaction is not commuting with the resting Hamiltonian, right?
Yeah, exactly.
Yeah, exactly. So I think this part, and together with the fact that the projection of the meter, which is here as Z, the projection of this meter along one of the axes is stochastic. This leads to actually decay of the averaged evolution. So in the end, you will see that while we are measuring the precession, we are destroying it, and we basically dephase it. So this is the main feature here.
Okay, so this is the same problem as in superconducting qubits, I think.
Exactly, yes. And I wanted to say here that analogy is absolutely full, because in superconducting qubits, you have this measurement back action based on the fact that you don't know. So you measure this n, which escapes the cavity at random position in time, and you don't know in which time. So that's why you don't know exactly the phase of the two-level system. So the more photons you allow in your cavity, the faster the two-level system decays. And yeah. So here I tried to exactly depict here this mechanism on the bottom. You see that there's the two block spheres. The one is for the NV center, for the meter, and another one is for the actual two-level system precession in IX equatorial plane. So we start with a polarized electron spin and SC, and then we apply just pivotal pulses to prepare it in SX, and then depending on the state of the nuclear spin, it precesses either to the positive or negative direction and acquires some angle alpha, which is controlled by the total time of dynamical decoupling. This rotation then is projected by another pivotal pulses to the SZ, and of course this projection again is stochastic. But what we can say is, let's say, if the electron spin was projected to the positive direction, then we can calculate what will be the net evolution of the nuclear spin in single operation of such protocol. And also we can apply the same mechanism to the negative projection. So what actually happens is that this IX, so imagine you start your nuclear spin in the thermal state. So after the evolution, you just acquire phase alpha, but it's heralded with positive and negative direction. Then during the measurement of the NV center, you have 50-50% chances to project to 0 and 1. And because the initial state of the nuclear spin was thermal, and when you project it, depending on in which state you project it, the nuclear spin polarizes slowly with a very small component proportional to alpha, either to the IX plus or IX minus, because your measurement operator was IX. Yeah, so this is this mechanism, and then let's say this is the beginning of our observation. Then we start precession between the two measurements, which is here depicted as these shadow errors on the right. And okay, if we were in the beginning projected in the 0 state, we're in the green sector, we precess gradually, and then we start another measurement. This another measurement is also acquiring some phase on the electron spin, which is then projected. And this projection is again stochastic, and which kinks us again to the IX direction to the same amount, which slightly disturbs our already acquired phase. So on this pathway, you can see that despite that you gain some knowledge about the precession, you also destroy it. Is everything clear up to now?
Yeah, that makes sense.
Yeah, okay. So then in our case here, we applied just conventional simple readout with green. So we obtain 0.1 photon per readout. And we can't see anything in the trace, of course, because the noise is much stronger. So what we actually do then is we apply the correlation, we calculate the empirical correlation between the photon counts. And we, let's say, run 1 coherent million of measurements, in which every measurement is perfectly timed with the frequency of the precession. And in the end, we can see such correlation function of the output. You see that despite that you see some oscillations which are related with IX, they are decaying, and the decay is mostly related with the fact that that you dephase it upon the random projection of the electron spin. And this is a very nice tool for example, making NMR spectra of such weakly coupled nuclear spins. As you can see here, by taking FFT, you can take the spectra, which gives you the precise position of the armor and the coupling of this spin. And also you can think about whether you can or not try to infer some information about non-commuting observables of such system. As I already told you, the IX does not commute with itself in time. And also because of this, you can recalculate using the just a Larmor precession, for example, IY at the previous position, you can recalculate through the IX in the next position. And with this, one can image, for example, think about reconstruction of the Wigner function or so for such a spin. So this is one thing about this weak measurement project. And what I also wanted to say is that if, for example, you can imagine or just dream about the fact that you precisely know in which state the electron spin actually have been projected, and there comes actually a different, let's say, figure of merit for this, because I point here this quantum limited measurement of mesoscopic detector, because this was, of course, discussed initially with the superconducting qubit, that if you try to measure something weakly, so that means unsharply, you don't destroy the density matrix fully to the thermal density matrix or polarized density matrix, but while you gain some information, you also dephase it, as we discussed. And the ratio of the information gain versus the rate of dephasing is called here the efficiency of the measurement. And there is a so-called ideal quantum detector or ideal quantum measurement where this ratio is 1. Of course, the strong measurement, the strong projective single-shot readout measurement is almost 1. But the question is whether you can realize the weak measurement also with arbitrary, let's say, strength parameter, having this efficiency close to 1. This is the tricky part. And I can explain you why. Because, as I already told you, if you want to make a single-shot readout, you have to use, associated with your electron spin, you have to also use the nuclear spin. So before reading out the nuclear spin, you swap the information or the state acquired by the electron spin to the nuclear spin memory. And after that, one can start to apply the single-shot readout technique to the nuclear spin memory. But this application requires a couple of thousands, as I told you, application of the green laser. And the green laser is very nasty in terms of disorder which it brings to the system. First of all, it could change the charge state of the NV center, which brings it into the so-called neutral charge state, which has completely different Hamiltonian with different couplings. And all of that is, of course, random in time, and it decoheres the target spin also. So the challenge here is that while you can try to apply this protocol, there is a certain trade-off between the fidelity you gain in the readout versus the decay you put into the target system. So what I was just interested to do is I applied such a protocol, and you can see that already with a small number of SSR readouts, we can see that the statistics of photon counts tends to split from Poissonian to 2 Poissonian, and this allows you already to distinguish in which state the electron spin actually was projected. So here in particular, I plot the data for the 300 SSR repetitions, and you see that we already have, by definition, single-shot fidelity, which is higher than 0.7, and yet the correlation function, which shows the decay of the target system, is not yet affected by this. So the decay lifetime is still same as it's for just one readout. Yes, so here is just, let's say, a summary of what we did. Here on the x-axis is the number of repetitions. That's the total number of application of the green laser. for different number of pi pulses. So KDD is, let's say, 20 pi pulses, and KDD5 means we apply it 5 times, so overall 100 pulses. And you see that fidelity grows sort of saturation wise with a number of SSRs, and decay time basically has a threshold when it starts to decay at the higher than 400 number of single-shot readouts. Overall, if we calculate together and bring all the parameters, we find out that actually this psi factor is not so bad. It's on the order of 0.5 for the moderate number of SSR repetitions, which is already quite exciting, because I think it's one of the first room temperature demonstrations of this ideal quantum weak measurements. Of course, this could be further improved if one could apply photon collection enhancing techniques such as solid immersion lenses, or maybe waveguides, or maybe some weaker coupled nuclear spins, which is actually hard to imagine. But I have to say the things are getting much simpler once you go to the low temperature within vCenter, because there you can actually apply very low power non-disturbing red light and excite it also spin dependent. Okay, so now with this I wanted to switch a little bit the gears and try to fantasize what could be potentially done if one have already a small register on nearby the NV center, like how one can apply the techniques available. So here what we have at hand, which is already developed for I think more than 5 years here in Stuttgart, is NV center and associated with 3 nuclear spins, which are very nicely coupled, such that all of them are resolved in the ODMR spectrum, so they are coupled stronger than the decay rate of the electron spin. And this allows actually to apply the before mentioned single-shot readout technique to all of them individually or jointly. And yeah, maybe I switch a bit the speed. So one important part is how one can initialize such a system. And one of the simplest, I would say, is by just measuring it. If you have a nice projective readout, you can measure it, and then already you see in which state you will have it. Another approach is to apply the electron spin as a source of polarization and transfer it, for example, via the swap operation or dynamic nuclear polarization if it's weaker coupled. So in reality, people use a combination of those to increase the fidelity and the speed of preparation. Other thing what could be done is how, for example, one can apply non-local gates to the individual nuclear spins. Of course, the nuclear spins, especially at room temperature, they are so weakly coupled that they hardly can interact on the time scale of T1 of the electron spin, which limits the overall time of the evolution there. But what could be done is the evolution between them via the electron spin. For example, to apply a C-naught, one can perform, so to say, such operations in which you conditionally on both spins switch the electron spin to the spin 1 where the hyperfine interaction exists, and then back. Just having this short introduction about the possible control, I just want to finally go to the possible non-trivial application, which is, for example, could be a QFT algorithm, so quantum Fourier transform, on these 3 nuclear spins. So a quantum Fourier transform usually is introduced as an analog to the classical Fourier or discrete Fourier transform, which I find a little bit confusing because if you think about it, discrete Fourier transform is actually allows you to do multiplex different frequencies, while quantum Fourier transform does not. This happens because here you have these amplitudes as a complex exponents, while for the discrete Fourier transform you have them as a so to say cosines, and then the difference between them could be imagined as a difference between summation of sinusoidals or summation of argument of sinusoidals. But here I just wanted to give you another view of that. So actually, quantum Fourier transform is just a nice transformation between the phase space and the population space of the register. So if you give, let's say, the register a certain state encoded with a phase phi, this phase phi with quantum Fourier transform, inverse quantum Fourier transform applied, results in a certain encoded register state. And here you can see how you really can interpret it as just a classical bit representation of a real number, and this is how I like to treat it. So how and where the Fourier transform, quantum Fourier transform and phase estimation algorithm is typically attributed to be used in sensing. So this relates to the problem of dynamic range in sensing. And in particular, if you just think about the sensing with a quantum object, you understand that if the phase acquired by the spin or qubit is more than 2 pi, then you cannot even resolve in which fringe you are. You have to do some calibration measurements in order to restore the global position of your phase. So this limits in the end your maximum range of operation of your sensor in terms of the B field, which you cannot sense. And because this is also related to the resolution of your, let's say, single measurement given by the projection noise, you have this fundamental limit associated to it, which is called the dynamic range. And why this is important, you can think of it is, so how it could be overcome is to combine several measurements with exponentially increasing duration, so that you can see different scales of oscillations in your sensor at the same time, or using several repetitions of the measurement. And then in the end, you can apply the inverse Fourier transform. This is the essence of so-called phase estimation protocol. And why it's interesting for sensing? So in sensing, already, as I discussed, that we have a nicely controlled register, we could have ability to actually sense the signals using the electron spin, but storing them in the nuclear spin. So this happens via such operation, which involves creation of the belt state between the electron spin and the nuclear spin. And such a belt state, after the application of the controlled rotation, acquires the phase on both electron and nuclear spin simultaneously, mainly because of the electron spin sensitivity. After that, the process of disentanglement, the phase is just stored on the nuclear spin and could be either read out or processed. So one can also think of applying similar protocol to the nitrogen spin, which is a 3-level system, and in that sense, instead of applying a 2-level Hadamard gate or pilot 2 pulse, one have to apply so-called Krestenstein gate, which is just a QFT also for 3-level system. So in that sense, this is just the way how we sense with our register. And now I want to explain to you how to apply QFT in such scenario. So imagine you combine all of this together and you try to imprint the phase from the external signal onto the different nuclear spin memories. In the end, what we see here is that we apply dynamical decoupling with different number of pulses during different stages. For example, for the nitrogen, we apply the most number of dynamical decoupling pulses, which results in 8-phi, 4-phi encoding in the phase. For the carbon-13 400, we apply smaller number, and then for the carbon-13 900 kilohertz coupled, the smallest number. So this results in the end in the state in the register which has this particular nice encoding with phase, which exponentially scales with index of the qubit. After the application of the inverse Fourier transform to such system, you can see that the final state of the register basically encodes the phase which was acquired. And this already represents the high dynamic range sensing, but of the external field. We can also apply it to the sensing of the nearby nuclear spin bus, and this is in particular, I think, important for the usage of this QFT, because having the nuclear spin bus, as I explained you already, leads to this quantum backaction and quantum effects, which appears as soon as you apply readout. So in comparison to the phase estimation protocols applied in quantum optics, just with photons, there is so-called this Kitife algorithm, where the phase estimation is basically realized with just one qubit. But in order to apply it here, you have to apply it, first of all, with a fast feedback, and then second of all, you have to, every time after the unitary, you have to apply the readout, which applies this backaction and dephasing of the whole box, which you want to avoid. And in reality, this question here is also actual for dynamic range, because imagine you have a nuclear spin bus, and in the nuclear spin bus you have different couplings, which result in, first of all, different frequencies, but second of all, also in different amplitudes of the signal. And that leads to the fact, if you, for example, have a very strongly coupled nearby nuclear spin, and you just spend your tau of the sensing, total time of the sensing, so that you don't saturate your sensor just with this spin on this background, on this large coupling, on the background of its coupling, you don't see the more weakly coupled nuclear spins. And so what you need is to make the tau very large, such that your sensor is at the limit of the T2, but you can still resolve different components of the frequencies. And this is how the QFT helps here to increase this dynamic range. So the answer to this protocol would be such a protocol in which you allow multiple acquisitions of the phase from the bus on different, which is stored on different memories, as I showed you before. And let's say the sensor works at the limit of its T2. And in this case, if you can still saturate all your qubits, that said that the most significant qubit in your register also being flipped, which is here blue, that leads to the benefit in this QFT approach, because basically what QFT here does, it just converts this longitudinal eigenstates of the register into the phase, and the inverse QFT converts the phase into the combination of the populations. So what you can do is simply acquire some phase, write it down into the register, apply QFT to store it in the classical population, which survives during the T2 decay time, and then you bring it back into the phase almost without loss of purity of the state to the register state in a phase space, and then you continue to acquire the phase after the big time. So this results in the end in the let's say a difference of two phases between initial and final time, or some means of correlating the phases acquired in the first sensing period in the second. In the end, you apply the readout, and you can see this correlated phase. So here you can see the example of this protocol realized before. I think I have not so much time to explain it here. I wanted just to quickly jump to the last slide of my talk. Is I think just a little bit of making the analogy and explaining better what QFT actually helps you to do in quantum sensing. Sorry. So imagine you have a different dimension of the register, let's say just 1 qubit, 3 qubits, or even 5 qubits, and you have just a complicated signal, which is depicted here on the right as red. And your task is to sample this signal in time and to basically record it, digitize, store it, transfer somewhere with a quantum sensor. So what you're doing is you're acquiring the phase in the Ramsey type of experiment, depending on the normalized signal strength, right? And after that, you project your spin, which has this phase, onto one of the axes, and you apply several trials to actually infer the probability distribution which is arising. And if you look at 1 qubit, let's say to reproduce here the signal reliably, I needed in the simulation 100 trials of projection measurement to restore at least to such level this signal. While for 4 qubits, I needed only one trial, and it's already showing a much finer reconstruction of the signal compared to the 1 qubit. So I wanted to say here that maybe the take-home message is that if you only have, let's say, few qubits, it's maybe already enough to demonstrate some interesting phenomenon, for example, in sensing, where you can apply protocols like Fourier transformation, and you can save a lot of time if your actual sensing takes a lot of time, or if you cannot, for example, reproduce a signal and you have to measure everything at once. Yes, I think with that, I wanted to thank you for attention and would be happy to discuss, answer your comment.
Thank you a lot, Vadim, for your very interesting talk. So now if there are questions, please unmute yourself. And go ahead.
Hi, so I would have a question. Could you go into some more detail, or could you just explain how I can scale up a circuit for quantum Fourier transform when I have 1 or 2 spins in my register versus 5 or 6? Like, what exactly needs to be changed?
Yes. So first of all, you need readout. So you have to find the ways to read out all of your nuclear spins. I think this is unavoidable because in the end, this is the register you want to read out. And to make this, you have to either increase, like if you use same protocols as I showed, with just C nodes, right, like this, you have to increase the coherence of your electron spin such that in a denser and denser spectral lines of these hyperfine, let's say, splittings further and further of nuclear spins, it's still resolved. So that, let's say, the natural winds of this MS0 is never higher than the splitting between the subsequent carbons splittings. So that is quite challenging, as I would say here, the splittings is on the order of 90 kilohertz, the smallest splitting, and the coherence time is 20 microseconds or so. So it's already on the edge. And I think the next coupled nuclear spin is 12 kilohertz, so it's already unresolved in this setting. But what you can do is you can apply this dynamical decoupling control and then readout. So this is possible, but then what happens then is that you read out not the IZ state of the nuclear spin register, but IX. So to read out IX state is maybe not always what you want. So, yeah.
Don't you have dephasing there?
You protect against dephasing also because of the dynamical decoupling, as the question was here before, because I mean mostly dephasing comes from IZ, and IZ you decouple first of all because of the dynamical decoupling. Yeah. So basically you average these quasi-constant terms in IZ because you flip the Hamiltonian up and down, up and down.
Yeah.
Yeah.
Okay, thank you.
So yeah, this was just about readout, but this already gives you the understanding. And then similarly, the problem in the readout is C0, right? And all other gates are also containing C0 as a measure for making this interaction. So to apply any interaction between individual nuclear spins, you have to rely on this C0. So that's why actually the group in Delft, they moved on to the low temperature. And in the low temperature, the T1 time of the electron spin goes to seconds. And you can just wait enough till the nuclear spins are interacting on their own. So I think they have now the register, of course, it's not fully coupled, but pairwise coupled to 10 qubits, 10 nuclear spins.
With nitrogen and carbon spins and the NV?
Yes, so they have NV as a, I think 9 carbons, nitrogen, and now they also recently established protocol to use nearby P1 centers, which are just electron spins. And they found 4 individual P1s, and they can entangle 2 of those together to create a bell state. It's becoming quite interesting central spin system, especially if you go to low temperature, then it's quite exciting.
Thank you.
You're welcome.
Okay, and actually for your QFT, which magnetic field were you measuring, and how important is the strength? Of course, it needs to be aligned, but just...
You mean when we measured the external field?
Yeah.
Here, so we just applied the field which we usually apply to drive nuclear spins. So it's quite strong field, and it's mostly oriented alongside, and it's on like perpendicular. So the actual component which was given the signal here is quite small.
Okay.
Compared to the other. Yes, that's why. Yeah, but because we just had this nuclear spin control, we just applied it also for sensing to calibrate the system.
And just before your slide of quantum register, where you had this figure of merit with KDD, can you just quickly go back there? just the slide before quantum register.
Yes.
How good? Yeah, exactly here. Did you try that with other sequences or?
So I think here the KDD plays important role, but not crucial. But I think we didn't try it with other sequences, though we tried other sequences for other things. I think in the end, we found out that the KDD is the most robust.
Okay.
So we tried with XY8 and KPMG. And the main problem actually happens because we have a triplet always, and our Rabi frequency is not much higher than the splitting. So our Rabi frequency is just 3 times higher than the splitting of the triplet. And that brings the large errors in the pi pulses because of the detuning. So the KDD here is important just to be protected from these errors. Yeah.
Thank you. Are there other questions?
Yeah, I might have one again.
Yeah.
So you show very nice results on these registers, and you're pointing out that there's other people that are also enlarging the size of this register around an MB center. But then, is there plans or already ideas on how to connect them?
Sorry, can you repeat the middle part of your question?
Yes, I mean, just there's very nice results, both from you when you were pointing out other groups are also doing similar work, where you can consider larger and larger registers, essentially like number of qubits around such MB centers. But is there plans to connect the registers? Is there already ideas on how to do this?
Yeah, I see. So yes, the ideas are there since a long time, but they're actually very challenging to realize. So the first idea, which was already published, is also in this group. It was realized to implant two MV center together, so that they are just sitting nearby and they are dipole coupled. So this, I think, though the results are there, the message from this work is that it's quite hard to make them deterministically and find these pairs actually, such that they are working stable, and also that they are, because in order to use the nuclear spins with them, you have to have them at the same orientation, and yeah, they have to be intrinsically with good properties already, while this is very hard to do with implanted NV centers. There is, of course, ideas to couple them via photons, and maybe some of you know the work from the Delft group, where they have performed entanglement between two distant NV centers by just measuring the photon collected from them. This is the approach which is also hard, because the NV center is not a good optical emitter. As people say, it has narrow lines at low temperature, but these narrow lines are moving because of the local charges, and it's very hard to stabilize them, especially if you have two of those, even more, especially if you would have more. But there are, like I wanted to say, yeah, there are new defects also coming, which first of all would have better optical properties, especially when it relates to implanted defects, and also, for example, silicon vacancy in silicon carbide. So there are prospects of finding dipole coupled defects, which would have different also optical lines, which you can address. If one could realize such a system, I think that would be a game changer, because such systems could be coupled to cavity efficiently, for example, and then they could combine the benefits of, let's say, two systems of superconducting qubits and on optically active defects by having, first of all, access to the optical domain and flying qubits. Second of all, they would have a cavity readout, and also spin-spin coupled. So they would have a much, let's say, more ways to connect them within the different register nodes, not only nearest neighbor connected. Yeah. So maybe I forgot something. I think that's are the prospects for the moment. And as I was telling already, this work from Fintaminio group, the recent work, it was very exciting result about actually controlling within vCenter nearby P1 centers. And because P1 center is basically like an NV center, but just without the optical readout, it also have intrinsic electron spin and it has nearby nuclear spins. So you can try to use this opportunity to already create a network of P1 centers where each of those would be the register on its own. So that would be my, let's say, full answer.
It seems like this integration to go towards cavity readout is also becoming more popular in the quantum dots world. So it seems like it's something that a lot of architectures are interested in. Yes,
I think I was just a couple of days ago, I was searching for one of the papers from the Bristol group for the quantum dots, but I actually failed to find it. I don't know why, but I think they presented. So the weakness of the quantum dot is that the spin properties, or let's say the memory, so they are very good optical interfaces, but they kind of lack this long-term memory. And I think there are a lot of efforts in this direction now. And if this will be realized, I think the system could have a nice.
Thank you for the great talk, by the way.
My pleasure.
So is there a last question?
But I saw here Philip entering.
Yeah, he's online.
I think most of the works I hear presented is also part of his legacy from here. Okay,
I think I see no more questions, so let's give Vadim virtual claps here. Okay. Thank you again, Vadim, and yeah.
Thank you.
See you.
Stay safe. Bye.
See you.